Okay, so this session is about rush measurement or rush analysis, and we will have both hands-on and also some theoretical discussion about where rush is coming from and what contributions it has made to the field of language assessment. I would like to start off by recommending this wonderful book. I think you will find your answers to many of your questions about measurement in psychology and by extension in language assessment. It doesn't talk too much about language assessment because measurement basically comes from other fields like psychology. So it would be a great idea to find out where measurement of personal attributes, measurement of psychological attributes come from, and how they have changed over the years. It would be interesting to know that the idea of measurement in psychology is relatively recent, and it was introduced in the late 1800s, closer to the beginning of the 20th century, where a group of physicists claimed that it's possible to use what they called the theory of errors in psychology. And basically the idea is, let's assume that you want to measure the distance between the Earth and a planet, another planet or a star. So you need to keep doing measurements. The first measurement that you do might have some errors in it. The second measurement might have less error in it. The third measurement might have more errors. So you can consider that there is a true measure of the distance between the Earth and a planet out there, and your measurements will fall around this true measure. So that's the mean of your measures. The more measurements you make, the more accurate the mean becomes. So the farther away those measurements are from the mean of the measurements, the more error you have in that measurement. This is how I can visualize it for you. So here, let's say this is the mean of the distance between the Earth, our Earth planet, and a star out there. So you make the first measurement, then the second one, the third one, fourth one, fifth one. And each time you have a measurement, you do not, so mean is the true distance. So each time you have a new measurement, you sometimes get the true measure, you sometimes get a measurement due to any reasons, which is a bit far away from the mean. And sometimes you fall here, sometimes you fall there, you know. And as a result, the farther you go from the mean, which is a true distance, the more error you have. This was an idea in astronomy, and physics, which was adapted into psychology. Then based on this, the classical test theory was developed. In classical test theory, you also have a true score, and you have some error, pretty much like what you see here. And this is what your observed score is. Okay, so this idea is still useful, but what Rush did was to change this idea a little bit somehow. And we are going to continue, we're going to talk about this we're going to talk about this today. So there's a question by Lizao saying, but when the times of measurement increases, the mean will change. The idea is as you make more measurements, you get closer to the true score. So the mean changes for the better. The mean becomes increasingly more precise. Does that answer your question?
Okay, I got what you mean. So, because at the beginning, I considered that the mean is equal to the true measure, but actually the true measure is objective there. And the more measures we did, the closer we are made to the true measure. And during this process, the means also change and to become more closer to the true measures, right?
Precisely. That's the point. So we perhaps we never know what the true measure is, but the mean gets closer to that. So we assume that the mean is actually the true measure because it's the closest thing to the true measure that we have. That's all we can get. So that's a good point that you raised. In this book, which is by a famous professor, Denny Borsboom, or Borsbaum, you'll see that he talks about 3 approaches to measurement. One is the CTT, or classical test theory. The other one is the family of structural equation modeling. And the other one is RASH and IRT. IRT stands for item response theory. So today we talk about RASH or RASH. Okay, so there is a lot more to the history of these models and all that. So what I'm not going to go through is really that history because it's going to take another course or more than one course to just talk about where these ideas come from and what they mean. Okay, so there are some measurement models that stem from Rush measurement itself. As I will explain later, George Rush is this gentleman. And he's the person who is behind what we call the Rush measurement. His basic model is this one. The first model that he proposes, this one. But this model was extended over time. And now you see that we have a lot more members to the family of Rush measurement. I am going to pause here for a while and ask you to take a look at these names. With the exception of these 1PL, these are not Rush measures. I will let you know in a second. Well, they might sound like some bombastic terminologies, but the basic idea is Rush measurement itself. It's interesting to know that when George Rush started to develop his model in a different parts of the world, that's North America, the United States to be specific, there were another group of scholars who were developing a very similar model. The interesting thing is that they didn't know that they were developing similar models. Rush in Denmark and what came to be known as IRT guys, IRT, item response theory. Let me write it down. Response theory. I hope you can read it. So item response theory guys, they came up with their own model. Now, just by coincidence, there is a very high similarity between what we call one parameter logistic IRT. And if I find time, I'll explain what that means. There's a high resemblance between one parameter logistic IRT and what George Rush or Georg Rush developed, which became known as the Rush model. So when you say the Rush model, we're referring to that basic initial model that Georg Rush developed. What is the specific feature of the Rush model? It's only applicable to dichotomous data. By dichotomous data, I mean the sort of data that you have indices like, or scores like 0 and 1. So for example, multiple choice questions or anything that is scored as 0 and 1. But this model itself is not applicable to rating scales like Likert scales. So if you have questionnaires, the Rush model doesn't work there. What works is rating scale model, but the principles remain the same. So if you know how the Rush model works, you can very easily extend your knowledge to the rating scale model, which is used for polytomous data, or the partial credit model, which is also used for polytomous data. So this one was developed by Anderson and the very famous scholar in Rush, David Andrich. David Andrich is a scholar in Australia now, and he's perhaps the most eminent scholar in Rush measurement today. There's a very interesting history to this. You know, Anderson and Andrich. When I'm not recording the presentation, I'll let you know a little bit about the history there. Anyway, so they're very big names. They have made significant contributions to the field of measurement. And then partial credit model, which was developed by around the same time by Professor Stone. And he's also working in Australia now. He's I think if I'm not wrong, he's an emeritus professor who is working for a governmental organization in Australia, if I'm not wrong. But I know he's still working and he's still active in this field. And then finally, the many facets Rush measurement, which was developed by Dr. Mike Lineker, a wonderful guy who is always ready to help. He's a developer of WinSteps, by the way. And if you have WinSteps, you can run the Rush model, the rating scale model, and the partial credit model. But if you want to run many facets Rush measurement, you need to use another software, which was also developed by Professor Lineker, called Facets. I have videos about facets, quite several videos. And by the way, the scores that you gave to your peers on their presentation for the first assignment of this course were all analyzed using facets. And all of you have now, by now should have received my comments and your peers' comments and a tentative grade and a table. That graph is going to be produced today, and you're going to make sense of it. Okay, so I'm not going to go through the rest of those models because they fall outside of the scope of this presentation. But if you're interested to learn about them, I mean, I have some papers which are published on these. You can go through my NIE profile and go through them if you're interested. Anyway, so I was talking about Dr. Mike Lineker. This is Dr. Mike Lineker, this gentleman here. And this is another guru in Rush measurement, Professor Benjamin Wright in red. Professor Benjamin Wright sadly passed away in 2015. It's very important to know that it was Professor Benjamin Wright who went to Denmark and brought George Rush to the United States. And actually, he made him famous, and he made the model famous. He was a physicist. And then I think he changed industry and went to psychology and those kind of fields. And he had worked with Nobel Prize laureates in physics, and he knew very well about measurement. So his measurement ideas seem to be, he found that they're in line with what George Rush was proposing. Anyway, so the Rush model itself has a lot of ups and downs in history. We have reviewed a little bit of history in two papers which were published recently, and one of them is your in your reading list. I hope you have read it for today. That's a comprehensive review of Rush measurement in language assessment. That paper took us around a year to write, or more, and it's the most comprehensive paper that reviews Rush measurement in the field of language assessment. We have done another comprehensive review of Rush across all fields. So we reviewed around 4,600 plus. Azrifa was one of the co-authors of that. Right, Azrifa? Was it you, or that was another? That was in language assessment. Okay. I just mixed them up. Anyway, so I'm going to pause here for a second and see if anyone has any questions. These were just really preliminaries, a little bit of history, a little bit of commentary, a little bit of description. But I thought it would be nice for you to know before you just dive into Rush analysis. It would be nice to just see who is behind it and where it's coming from. Any questions so far? Good, no questions. Okay, I've talked about this. So I talked about these three: Rush measurement, IRT, structural equation modeling. Anyway, Rush measurement is a probabilistic model. What does that mean? It's talking about probability. And also probability of what? Probability of the person or the test taker with ability BI to answer an item with difficulty of D. So your probability, that's P subindex ij, your probability P of answering an item with a difficulty of D and with your ability as B is estimated by Rush measurement. So that's as easy as that. So if you, let's say you have this line of difficulty and ability, diff ability. So if the item is here in terms of its difficulty, whereas you're here in terms of your ability, this is item 1, this is item 2, okay? And this is you. A very happy test taker who doesn't know what's going on. So question, this happy test taker, would you say that he or she has a higher probability to answer item 2 correctly or to answer item 1 correctly? And this is the line of difficulty. Easy items are at the bottom, difficult items are at the top. Difficult, sorry for, okay. Can you open your microphone and answer? Does anyone answer that? Because I don't hear anyone speaking. Hello.
Oh.
Okay.
Yeah,
sorry.
I guessed one.
So which one would be easier? I mean, have a high probability to be answered?
Yeah, I'm guessing
Item
question one, yeah.
Because?
On the difficulty scale, it's easier.
Exactly, precisely. I mean, this sounds to be so easy and so intuitive that you might say, what's the point? Of course, just one of the items actually. So it's the item that is easier. That's, you know, and in the same way, you can turn around the scenario and say, which item has a high probability to be answered correctly by this guy?
Question one.
Exactly, in the same way, 1. Because it's easy, so it has a higher probability to be answered correctly. And that's the whole idea. That's all mathematics we want to talk about today, really. So we won't talk about math anymore. We just talk about the practicalities and how to use rush measurement, okay? Now, of course, if you're curious what other models, I mean, I reviewed them here, the rating scale model and the partial credit model are, they only add one more parameter, and this is called the step parameter, or the tau parameter is written in this way. It's like something like a T or tau parameter. It goes by different names. I'm not going to cover it in this session, but if we find time, hopefully I will talk about it later towards the end of this session, if we find time only. I don't make a promise, though, but if you're interested, I'm always happy to have a chat with you about it. There are two important assumptions of Rush model: unidimensionality and local independence, and we will talk about them. So for your Rush analysis to make sense, you need to make sure that your scale or your test is unidimensional and your test items are locally independent. So unidimensionality is about the entire test. Local independence is about the test items. The questions are locally independent. And again, I talk about these in details as much as time allows. I should let you know that this session is an introductory session to Rush measurement, by the way. So let's not expect too much, because you know, there will be a lot more left about Rush measurement. Like I said, we will need a full course to talk about Rush measurement, but this session is designed to help you understand the papers when you read them and run some basic analysis on your own. I think this will be pretty good enough. And I'll be honest with you, not many people in the field of language assessment will have the skills that you will develop by the end of this session. So I think from this perspective, in my opinion, and I might be wrong, in my opinion, the session is going to be quite useful, even though limited. Okay. So when we run the analysis, there will be a bunch of things that we need to check. And this is a list. It's not an exhaustive list, but based on the literature review we carried out recently, which was published in language testing, this is what most often most people in language testing present in their papers. Not everything will be applicable in this data set that you have, but it's good to know that these are important. Okay, so now I'm gonna exit my slides. Oh. Exit. Okay, I'm gonna exit my slides. I'm gonna start doing the analysis. Before that, I want to figure out if you have any questions, everybody. No questions? Okay.
Can you explain the assumption of unidimensionality and local independence a bit?
Yeah, as I will go through the analysis, I will explain them in details.
Okay.
I mean, I want to show you how they work within the software, then it will be more meaningful to you. Okay, I think you're still able to see my screen. Am I right to think so? Good. We have 3 data sets for today. I have downloaded them here. Can you see them? Okay. I would like to start with the first data set, week 12, data set for Rush modeling. And it's data from 240 students in Singapore. And they have taken 15 test items. I have sent you the 15 test items. Do you still have them? And I was expecting that you will go through them. I hope my expectations are met. You would go through them and figure out which item, just, come up with a rough estimate of which item might be the most difficult one and which item might be the easiest one, and kind of rank order them based on their difficulty. I hope you've had a chance to look at the test items. This is what we practiced last session. Do you remember the Mumby's way of speculating the item difficulty in the reading test, which we read about the dancing and drums and all that? So he had come up with some assumptions about the difficulty level of those items. Today, we want to do the same thing, but we want to follow up about the assumptions and validate those assumptions to figure out whether our assumptions work or not. Okay, so it's not enough in test validation. It's not enough to assume that your test items have a hierarchy of difficulty, but you must have proper evidence to back up that hierarchy of difficulty that you have built in your mind. Where does that proper evidence come from? It comes from the actual data that you collected from your students, and you subjected it or submitted it to a Roche analysis or other types of analysis. Okay, so let's get started. Do you all have WinSteps on your machines? I hope so. So the first thing is that you see we have different types of data: Excel sheet, SPSS, and Excel sheet. WinSteps does not automatically read them, so we have to convert them to WinSteps friendly files. So first of all, let's open WinSteps. Okay, this pops up, and some of you also have this little window that's there. Do you also see that? Okay. If you can't see this window, this little one here, click on Excel RSSST and you will see it. So that's the first step towards our data analysis. Okay, so far, I think you can guess the rest of the steps because we have an Excel sheet here. Can you see that on the today 5? I want to read that using the Excel button. Click on Excel. This will pop up. Select Excel file. So now what you're going to do is to find that Excel file on your computer. Here, this is where I found it. So I'm going to click on this one and open it. It's going to take some time depending on how fast your computer is. Okay, for me, it's open now. Did you open it, guys? Good, you're all there. It's very easy steps. Now, we have two sections: item response variables, person label variables. Okay, so let me open it again, just to remind you of what we're looking at. Like I said, we have got 15 items. These are item specific. And the first one is for students. It's an ID, student number 2, number 4, number 5. Sometimes you have gender. Sometimes you have other things. So you regard them as student, but the test scores are regarded as items. So I'm going to close. Oh, there's something else that I just noticed. As you see, our data is not dichotomous. It's 2, 1, 2, 0. We have got 3 somewhere here, so it's not dichotomous. I'm glad I found it. Okay. Let me look at this data set. Hold on a second. This is supposed to be dichotomous. Yes, so this data set is dichotomous. It's got 40. Okay, guys, so a change of plan. Let me see. A change of plan. Let's close this one and cancel. Go back to Excel RSST. Excel. In the same way, select Excel. Let's start off by looking at this one. Week 12 Rush Modeling Dataset 2, please. Okay. And click on this. And your data will open in a while. Good. So if you're curious what this data set represents, it's basically data set from the administration of an IELTS listening test. There are 40 listening test items or 40 questions. So I'm going to highlight all of these 40 items all the way down up to number 40. Okay. And you can either copy or cut. I'm going to cut it. Doesn't matter. Copy or cut.
Professor, I'm afraid we don't have this data set.
Oh, it's available actually. We made it available at around 4 o'clock. Please go to
Until you learn.
Blackboard and you can until you learn and you can download it. Okay, so I'm going to wait for a while, but just to let you know, I have already cut those data and I'm going to paste it under item response variables. If you download it, please let me know so I can continue.
So we just cut from question 1 to question 40, right?
Yes.
Okay.
If you want to analyze fewer questions, you can only cut those questions that you want to analyze. For example, you say, I want to just analyze 10 questions. So you just cut and paste these 10 questions.
If we copy and then it remains on in the original, does that change the analysis?
No, here?
Yeah, and it
No,
remains
it doesn't change it, no.
Okay.
Because WinSteps only reads this spot, what is under that and what is under this.
All right, thanks.
Yeah, sure. Now, if you're interested to get for example, one of these person variables like the nationality or age, you can just cut and paste, or really drag and drop also works. Some basic Windows operation stuff, nothing very difficult to do. And the way why I do not include the rest of these items here, because they are not items. They're not test items, they're something else. Okay, so far, guys, can I check if you downloaded everything? And
Yes. Right. Thank you.
very nice. So by now you should have item response variables, 40 of them. I leave it to you to decide whether you want to analyze all 40 items. I suggest you do, because then we will be looking at the same output. Then person label variables, and then construct WinStep file. Just click on construct, and this window pops up. I'm gonna save it on my desktop. And I'm gonna call this, for example, IELTS 1. And you can call it anything really. It's gonna be a text file, so save. And you see it's saving, you see those lines? Good. And it opens. See your data is here. You should go take a look at your data. And as you see, we have some missing values here because in the original files, the This is nationality. This is age. So we don't know the age of the first person, but the nationality of the first person is number 1, whatever that means. It could mean Chinese, it could mean Iranian, Singaporean, and we don't have the age of this person here, as you see, and so on. So the data is here. Now, what you should look at is this code here. Always check this, please. Make sure that you don't have extra codes, because your code is supposed to be 0 and 1 only, which matches the data. It's dichotomous. So if you have a 2, and if you do not expect a 2, then you have a problem there. You should go to the data, find that 2, and correct it, because that little 2 will affect everything. You can't imagine just 1 or 2 miskeyed in data, what they can do to your analysis. They can make everything totally wrong. The rest, you can just keep it as is. I mean, these are some codes. You can just leave them as is. And almost always this output is correct. If your main input is correct, this file is almost always correct. I've never encountered any scenarios in which there is a wrong output by WinSteps. It's very
Can
smart.
I have a question?
Yeah.
After the codes, I mean, after 0 and 1, there is a blank. Does it referring to the missing data?
Well, that could refer to, let me see if I have missing data. I don't think so. We don't have any missing values there.
Okay.
No.
So it's natural that there is a blank after 0 and 1, right?
Yeah.
Okay.
Most likely it doesn't refer to anything. I don't see any missing. But sometimes if you have missing data, it's represented by a dot like that. But it's not anyway. So I'm going to close this. I don't save it because I was, okay. So we can end this because we don't have anything else to do here. Now I'm going to close WinSteps. And look, this is the data I created. This is what I was looking at, if you recall that. Now, there are 2 ways to open this data set. The easiest one is just to drag and drop it into WinSteps like that. Try that on your computer, and this should pop up. Drag and drop it into WinSteps. Okay. I think probably you have done that by now. Now, what we need to do is press Enter once and press Enter for the second time. The magic is happening. There we go. Okay, guys. Can I check if everybody did this?
Yep.
Good. So this is probably the first rush analysis for some of you.
Dr. Vahid, what do we press again after we open the file? I missed that step because I was trying to drag and drop and it didn't work.
Okay, drag and drop, then WinSteps opens.
Yep.
Press Enter twice.
Enter. Okay.
Enter
If we
twice.
don't drag it, how can we?
Or you can open it from File. File. Open File. You can just open WinSteps first. It's going to be like this. Let me just do it once quickly. So you open WinSteps. There's nothing there. Go to File. Open File. And find your input. Mine is here, IELTS. It's open now. Click, press Enter once, second time. Okay, you should press Enter twice. Very good. Okay, pop quiz. I have a second data set. Week 12 data set for Rush modeling. Convert this into a WinSteps input file. I'm going to give you 2 minutes. I'm going to pause recording. So on top of the hierarchy is item 38, which is the most difficult item. What is the second most difficult one? This one.
36.
Exactly. Now scroll down and give me the easiest item.
8 and 9.
8 and 9. There's a little bit of visual deception here because they're probably not exactly at the same level of difficulty. We should look at their indices. But the right map is not the way that you see it from here, is not highly precise. So even if item 8 and 9 might have slight differences in their difficulty, they are put on along the same line, horizontal line like this. But they could be slightly different. I mean, we will look at that in a second. Now, these X's represent persons. Sometimes one X represents one person, but if it represents more than one person, for example, 2 or 3, you will see a comment here at the bottom saying that every X means 3 persons or 4 persons, but we don't have that currently. So take it that every X is 1 person. So this guy, whoever he is the least able test taker among the rest. And these guys are the most able ones. Okay, so far?
So X mean 1 person, right?
Yeah.
What does this 4, 3, 2, 1 mean?
Okay, I'm going to explain that in a second. Okay, now we have, before that, I need to tell you something else about the line. We have T, S, M, and again, S and T on the right side. And on the left side, you can see the same thing, right? Can you see them? TS. Right. Now, the first, I think the easiest one to digest is M. M stands for mean. The mean of persons. The mean of items is here. Okay. Now, the mean of items is slightly above the mean of persons, the mean score. The average score. Mean is the average score, by the way, right? So it doesn't mean that on average, items are easier for people or items are more difficult.
More difficult.
Difficult.
Good, because the mean is higher. So this is one of the cool things that Rush measurement can provide you with, the mean of the items and the mean of the persons. Now, for those of you who have taken the research methodology course, I think you should remember the standard deviation. Do you remember that? I mean, some of you might not have taken it. So I think I won't explain too much, but standard deviation is a yardstick, sorry. It's a yardstick, something like this, okay? So you can say that this is the mean, this is 1 unit, 1 standard deviation, then 2 standard deviations, then 3, and so on. So some items fall in this region. Okay, so they're 1 standard deviation above the mean. Some items fall 2 standard deviations above the mean. They're very difficult. So the items within 1S standard deviation are these: Q17, Q11, all the way up to Q34. Okay, I can't just highlight one side of it. Let me see if I can. No, I can't. Anyway. Is that okay, guys? Now, on the left-hand side, you can see the people with 1 standard deviation above the mean of people. And their x's, these guys here, all the way up to here. Now, the rest of them are 2 standard deviations between S and T. So they are within 2 standard deviations above the mean. They are variable, and these items are very difficult because they fall between S and T. So this is the basic idea that we need to take away from this map. And finally, there's one more thing that I wanted to explain. These numbers, this is like a ruler. Okay, so what does it mean? These units are called, let me go back to, you don't have a right map here, but anyway, I write it here. Those units are called logits or log odd units. They are the same thing. Logits or logits. And what is a logit? It's a transformation of the raw score to a different unit, which is logarithmic. Now, don't panic. It's nothing too difficult. All of us have got calculators on your phone. If you open the calculator, let me see. Okay, I opened the calculator. If you open the calculator, you can see a button called log n. This one, can you see that? Log n. I don't know if you can see that, but if you enter any number, for example, 20, then press log n, you'll get a smaller number. Okay. What did you get? What did you get after pressing 20 and log 10?
1.3, is it?
Yeah, exactly. So what log does, logits do, is to shrink the numbers. So currently we have 40 items. So you can have any score between 0 and 40. Logits shrink them. And one of the cool things about logits is, where is my output here? Not only does it shrink them, but also the units become the same. So units from 0 to 1 have the same distance as units 1 to 2 and units 2 to 3. The distances are the same, pretty much like a ruler in which you've got centimeters. Now, this is one way of converting raw score to interval data. Again, those of you who have taken methodology, research methodology, know what I'm talking about. So Roche measures are very useful interval data. Even though raw scores, you might argue, raw scores are also interval, but some people do not agree. Because, for example, the distance between 32 and 33, which is 1 unit, is not the same as the distance between 54 and 55. So, we convert them into units. I think that's all we want to know. So if you're still not very much sure what logits are, just think about it in this way. They just mean two things. One, item difficulty. Two, person ability. So for example, these persons are 1 logit able. Okay, it's like they're 1 centimeter able, something like that. And this item 29, is slightly more than 1 logit difficult, because you see this is 1, so 29 falls above that, slightly more than one logit difficult. What item is 2 logit difficult?
27.
Exactly. What item is 0 logit difficult?
30.
30.
38.
30, yeah. That's
30.
That's 0 actually. And so on and so forth. You can see that these people are -1 logit able. So it's something that runs from -infinity to +infinity. Okay, guys, so far? Okay.
So what does -1 mean?
-1, it doesn't mean it doesn't exist. It just means it falls 1 unit below the mean of the items, because the mean is 0. We fix mean at 0. So we convert it using that logarithm button to 0. So if you look at item 30, you can calculate the difficulty just manually in the Excel sheet and then bring it to your calculator. It probably gives you something close to 0. So -1 in items simply means it's 1 unit below the mean of the items.
Does
Does
it
it mean it's easy?
Oh, okay. So now the concept of easy and difficult is relative here.
Okay.
It's easy for some people. It's difficult for some people. So item 30 is given to these people. Is it easy or difficult?
Difficult.
Very difficult. Do you expect that these people answer the item correctly?
No.
Probably not, because they need to be very able. Now, item 30, is it easy for this guy or not?
Yeah.
Yes,
Easy.
it's easy because he's way above that. This is 0 logits. He's more than 2 logits able. So do you expect that this person will miss the item?
No.
No, he will not miss it, probably. That's why we say Rush is a probabilistic model. So it calculates the probability with which this person should answer this item. So it probably says this person probably has 80% of probability to answer the question. So we expect that this person will answer rather than miss the item.
How can you get the accurate percentage for the probabilities?
Sorry, the accurate percentage of what?
You just mentioned 80% chance to answer this question.
Oh, you can output it from WinSteps here. I can output it later for you. It's in one of these options. I should go through this. You can output that probability estimate. And you can also, not only that, but Rush also tells you, so based on the probability I've calculated, I expect that this person answers this item, gives it a 0 or gives it a 1. So it depends on your ability and the difficulty of the item. Do you remember? This is what I just mentioned. Where is that? Here, probability difficulty. So they probably are starting to make more sense to you, or new sense, new kind of sensing meaning. So that's what I mean. There is the concept of probability behind everything. So don't worry about the map. There's something that you can understand better. I hope you have, if you have understood the map by 60%, that's just pretty good enough. So there's a few things that, there are a few things that you should take away from the map. And that's, there's a hierarchy of difficulty on the right side, hierarchy of ability on the left side. There's a mean for each side. And the things that fall on top are more difficult on average. Things that fall at the bottom are easier on average. And in the same way, able is there, less able is at the bottom. That's the most important things that you need to take away from this map. The other map is the same map, but it has been flipped around, flipped upside down, in other words. So here, easiest items fall on top. Difficult items fall at the bottom. Why is it so? Because Mike Lineker thought that some people can understand this table better than this one. But for me, I always look for difficult items on top. Okay, guys, so let's go to output tables. So that was number one. Number two is output tables. So number 10, 13, 14 will give you the same thing, but they have been arranged in different ways. So let's go through number 13. The items have been arranged based on their measures. Okay, did you get this table? I'm going to do it again. Measure. Click, and there you go. You can see all the items you have in this table. Items 39. Can you see that? It's right on top. At the bottom is item number 9, and then number 8. Like I told you, they're not exactly the same, of the same difficulty, but slightly, they have slight differences in their difficulty. So the most difficult item is on top. Any questions so far?
But that's in fit and out fit.
Oh yeah, don't worry about it. I'll explain them. Okay. So what do we need to read in this table? There are just a few things that we need to know. There's a lot of detail here. I don't want to, like I said, I want to give you a basic but useful understanding. So I don't want to bombard you. Of course, item number. So that's number 1. Number entry is 38. It's the same here and here. Okay, so far. Now, the total score is 18. What does it mean? Let me write it down here for you. Hold on a second. Here. So total score. Number of people who answered the item correctly. Oh, I'm running out of battery. Okay. Okay, guys, so the number of people that answered the item correctly, that's the total score. 18. Out of how many? Out of 209. So only 18 people got it correctly. You can imagine how difficult that item was. So now I want to use a calculator again. Calculator. Okay. Hold on a second. Okay, good. Now, you see 18, 8 out of 209 answered it correctly. This is okay, 0.08, let's say. 0.08 is the difficulty of the item. Okay. Now, if I convert this to logs, you don't get exactly the same as 288, but let's see what we'll get out of it. It's -1. Yeah, it's not exactly like log because the log in WinSteps is different from this log here. But anyway, so what I wanted to say is that let me write it here so you can visualize it better, that 0.08, which is the raw difficulty, is converted to logits, and we get 2.88. 2.88. So here, 2.88 is the most difficult item among all. In the same way, you can, for example, convert this one. Let's quickly do that as well. 22 divided by 209 equals this, 0. almost 10. So 0.10 to logits is 2.60. 2.60. Okay, so every difficulty, every raw difficulty has a logit conversion. You don't have to be a physicist to know this, because you know, when you're measuring temperatures, you can do the same thing. For example, you can change Celsius to Fahrenheit, or Fahrenheit to Celsius. It's the same thing. This analogy is very useful here. So you're changing something like Celsius or Fahrenheit to another unit of measurement. Why do we do this? Because it makes the data more understandable and easier to make sense of. So the measure of the first item is this. So this is the second thing we need to know from here to here. Do you have any questions so far? Okay, don't worry if when we do the hands-on, you'll get to know it better. Okay, next thing is this model standard error. What does it mean? So look, I've got this 2.88. I mean item difficulty. Let me in my sample. Okay, now do you remember, guys, those who are taking MAE 900? Do you remember we have a concept called population? So we don't just want to know the item difficulty in the sample. We want to know the item difficulty in the population. In other words, if you give this item to a large number of people, because that population is what we want to measure exactly. Not just my sample, not just my classroom, but the sample. Why sample? Because that will become the true difficulty. or the standard difficulty of the item. Okay, so now I'm asking you this question. Do you think that this item is in the same way difficult in the population or not? How certain are you about it? How certain are you about this number that you gave me, about this number? And you say, okay, I have an answer for that. I can give you a range. I can't exactly give you the difficulty in the population, but I can give you a range of difficulties within which the difficulty of the item falls in a population. But I know the difficulty in my class is 2.88, but I can't give you exactly the population because I don't have access to it. But I give you a range, 0.28. Okay, that means in this population, my item falls between 2.88 plus minus 0.28. So if 2.28 is here, my class, in the population, the difficulty falls here. It's 28, 0.28, 2.88 plus minus 0.28, which means, can you calculate that for me, please? 2.88 minus 0.28?
2.60.
2.63
60.
and 60. And what's the upper bound? Plus 288 plus 228.
3.16.
3.16. Okay. So now you're saying that the actual item difficulty in the population falls between this guy and this guy. But what is it? We don't know. There's an interval that I can give you. Now, is it a big interval or a small interval? The point is, the smaller the interval, the what? The smaller the better or the worse?
I don't know.
Because?
They're more reliable.
Exactly. Because I have more confidence. I'm closer to it. But if I'm 3 kilometers on the right side away from the score and 3 kilometers on the left side away from it, I don't know where the exact score falls. It could be anywhere here. And it's not necessarily the mean. It could be anywhere. So the smaller this interval, the better. In other words.
So, Dr. Vahid, is it a coincidence that the most difficult question has the highest standard error as well? Is that normally the case?
Great question. It's not a coincidence. I have 2 answers for that. An easy answer and a more detailed answer. For the easier one, I'm going to give you the easier one now. If you notice, those items that are very difficult or those that are very easy at the bottom have higher errors of measurement. Standard error, SE is standard error. That means higher uncertainty. Why is it so? I can talk about it later because, you know, I have to digress and talk about some other concepts. But keep this in mind. This is usually the case. So the easiest items and the most difficult items always have a lower precision in their difficulty level. Something that we can never be able to speculate just by looking at the items. Okay, so we need to have actual measurements like this, Roche measurements, to tell us what's going on. This is a huge advantage that Roche offers. It gives us the difficulty, but also the amount of certainty with which that difficulty should be interpreted. Okay, guys?
For the measure, I see some figure with minus below. That's it.
Sorry?
For the figure for measure, with there's some figures below with the minor, like minor 0, like yeah.
Yeah, so these are those items that fall under 0.
Yeah.
Yeah, so you just plus minus 0.16. Yeah, is that your question or?
So I don't understand about why it is minor, or is it below the mean or something?
It's below the mean, right?
It's below the mean. So it's below the mean of the items. Sorry, where is the items? Here. Go back to. So these are these items here. 22, 25. Anything that falls below the mean is minus. You know, so why is it so? It's simply because we changed the row difficulty, as you see here, to logarithm, to logits. Okay, so when you change them, some of them become negative, some of them become positive. Is how logits function actually. It's, you know, how the mathematics works.
Thank you.
Sure. So I'm going back to this one. Now there are two more things that we need to know, and there will be a lot of details about them, but I'm going to give you the most useful one for this session. I would expect that you will have questions. That's fine. I'll try to answer your questions as much as I can. But what is the most useful way of looking at these? One of them is called infit. One of them is called outfit. Okay. So I'm going to add another slide here. So far, we have learned that item difficulty has errors, standard error. This is certainty. Of course, personability has the same thing. Item difficulty can also be accurate, not accurate representation of the difficulty. What does it mean? Okay, so I give you an example here, guys. Let's say this item, we know it's difficult, right? We all agree on that because it's on top of the hierarchy. It's very difficult. It's the most difficult one. Now, imagine that a lot of people couldn't answer this question, not because it was not difficult, but because there was a typo in it, or there was another problem in the test item. So the difficulty is not caused by the ability of the person, but by something else that's not supposed to be measured. Okay, so when something else affects difficulty, we have a problem. And as I said, this something else can be anything. If you recall, we had sources of construct irrelevant variance. If you don't remember this, I just want to simplify it for you. Anything else includes things like typos in the test items. Sometimes students cheat. Sometimes they miskey in their answer, etc. So it's something else that should not affect my performance, my ability, but unfortunately, there is a problem there. That problem affects my performance. I give an example. If you are taking your blood pressure as an example, if the machine is not working properly, if there's a glitch in the machine, then what you see, well, you can see my blood pressure is this, but that doesn't make any sense. It's not accurate. Why? Because the machine is not correct. It has a glitch. Or even if the machine is okay, perhaps, for example, there's too much, I don't know if the noise affects blood pressure, or there's too much, you have taken too much coffee, or there's too much noise, or I don't know, the temperature is too high and you're sensitive to high temperature, then that affects your blood pressure. So the index itself is not very much accurate anymore. It's good for nothing, in other words. Now, how do we know if the index is good or not good? Can we say it's accurate or not? We have two ways of looking at it. They're called infit and what? Outfit. So in other words, I want to put it in this way. Okay, now that we know that we have a difficulty measure, this here, and we know the certainty with which to make sense of that difficulty measure, but the question is, does this difficulty measure really reflect difficulty only, or is it affected by something else that we don't know? Then Raj can give you some ways of quantifying whether that difficulty measure is accurate or not accurate. Okay, so one of them is called infit, outfit. The other one is called outfit. Now, look, infit has got MNSQ, ZSTD. Outfit also has got MNSQ and ZSTD. Now, a lot of people do not find ZSTD very useful, so let's just stick with MNSQ for this session. So infit, now MNSQ stands for mean square value, MNSQ, MNSQ, mean square. Okay, now as to what is a mean square, that's a different story. You know, I don't want to go to too much details. Remember that this is a basic session, but for those of you who are interested, you can look into chi-squared tests, because MNSQ is similar to chi-squared test. But if it's too much, just forget it, please. What you need to know to make sense of the data that you read in a paper, and also your own data set, is this. Very easy, very straightforward. I have tabulated it here for you. I don't want to do it again. I mean, to write it. Gosh, where is that? So everything you see, most of the things you see here, I have gone through, and this is the definition of fit statistics. This is what I'm looking for here. So for infit and outfit mean square values, the best thing to happen is that they are between 0.5 and 1.5. A good analogy is that if they're between 0.5 and 1.5, you hear music. What comes from the data is music, meaning that you can make sense of it, meaning that it's accurate. Everything is more or less in place. So those difficulty measures that you saw are accurate. Is this accurate, roughly? Is it? Based on the infit MNSQ, is it accurate?
Yes.
Because?
It's between 0.5 and 1.5.
Exactly, it falls between 0.5 and 1.5. Now, outfit, how about outfit?
It's just under 0.5, right?
Slightly under 0.5. For, how about this one? This is easier to make sense of. For item 36, infit MNSQ is this, outfit mean square is this. So would you say that this is reliable, accurate, or not?
Yes.
Yes, so this 2.60 is accurate and we can rely on it because of this and this. All right, guys, I think you should now be able to make sense of it more. So let me also do another visualization for you. I think I'm a fan of visualization. Look, so we can't do it here. Gosh, here. Yeah, okay. Can you see this? This is the same window you were looking at. So we always look at the measure and we say, okay, I got the measure. I know the measure in population, the interval. I know that now. Now, is this measure correct? Yes, it's correct. Yes, it's correct. In the same way, I'm just randomly choosing this. This is the measure. This is the interval in the population. Is it correct or not? Based on this?
Yes.
Yes.
Correct.
And this?
Yes.
Yes.
Yeah, okay. Why? Because it's simply falling between 0.5 and 1.5, as you can see from this slide here. Now, the interesting thing is, if it falls below 0.5, it's still fine. It's less productive. It's not degrading. You still hear music. But you see, may produce misleading high reliability and separation. So it's not a bad, too bad thing. It's still okay. I mean, we won't lose too much if it falls below 0.5. But if it falls above 1.5, that's where the problem starts. It's unproductive. It's still not degrading. Nowadays, we say it's still really bad. It's beginning to become degrading. But if it's above 2, then we have a problem. Now let's look at our data here to see if we have a problem. Look at these statistics. Do you find any problematic items based on infit mean square values and outfit mean square values? I'll give you 2 minutes.
No.
Are you sure?
Question 3.
Question 3, okay. Because?
Outfit is more than 155.
Yes.
8 and 9.
This one is a bit problematic. Which one? Sorry.
8 and 9. The
8
last
and
two.
Yes. Okay.
19 and 14 as well. He has a score of above 2.
Yes. You see, while the outfit is a bit problematic for some items, infit is still fine. One of the reasons why sometimes, now some details, by the way, you can note this down, by the way. One of the reasons why outfit sometimes goes crazy is that a very easy item is missed by high ability people. For example, the item is so easy, I'm not even looking at it, I'm just closing my eyes, it's so easy, I can answer, I can, meaning that, I'm just putting it in a silly way, but meaning that the item is so easy that the test takers who are highly able do not even bother to concentrate on the test items. They don't read it well. They say it's very easy, let's just move ahead. They miss a few easy items. And like a few high ability people miss that easy item, and that becomes a red flag, a little bit of red flag. On the other hand, sometimes a very difficult item is given to a low ability student, or some very difficult items. And that low ability student is not expected to answer the question, like 38, which is at the top. The person is right at the bottom, right? So he is not expected to answer this difficult item. But what he does is he looks around and he looks at his friend's paper and he's saying, oh, that's B. So let me write it down, B. And if a few mishaps like this occur, then Rush flags them. Say, hey, we have a problem here. This item has been answered. The word is erratically. So I want to write it down here. For these, the item has been answered erratically, meaning that the Rush looks at it and says, I can't make sense of it. Something is going wrong here. Red flag. Okay. So in this session, guys, that's the only thing we need to learn. Let's not bombard ourselves with too much information. But these are, I've been doing Rush measurement for quite a while now, for quite a few years. I can tell you that these are the most useful things that, and the most important things that we need to consider when we are doing Rush analysis. So let me wrap it up for you. You look at the total score. It's not Rush, it's just the raw score thing. Total score and measure. Standard error. Infit mean square values. Outfit mean square values. I think that should be just good enough.
What about the ZSTD?
I didn't want to go through them, but they range between the acceptable ranges between -2 to +2. But nowadays, not many people refer to them because they get inflated easily because of the sample size. So if you have a large sample or a small sample, they can get inflated very easily. So they cannot be very much reliable. The easiest ones are these, the best ones. So you can stick with infit and outfit range. One last thing before we take a break. I know it's not here. Okay, I think we can take a break now for a few minutes. Then When you come back, we'll do hands-on, and we'll see what else we can cover in this session. You can go through the slides. Okay. So how about 15 minutes, guys? Come back in 15 minutes. Let me pause. Okay, recording started. Since we have now learned some basic concepts underlying Rush analysis, what I would like you to do is to do hands-on now. So I'm going to put you in groups. We're going to open the breakout rooms. What you need to do is to look at the second data set, which I didn't analyze. It's also an Excel sheet by the name of week 12 data set for Rush modeling. Yes. Okay, data set for Rush modeling, week 12. I'd like to look at that, convert it to win steps and run the analysis, and also speak with your friends about the difficulty of the items. Now, during your chat, what you need to talk about is the actual difficulty or the measures of the item and what you speculated before, because these are the items that you looked at before. Okay, the items that I sent you, those 15 test items. So then you can compare the actual measures and what you speculated in the past. Do you think that there is a relationship between them? In addition to that, please talk about the fit, infit, and outfit mean square values, the standard error of measurement, etc. Now I'm going to give you 25 minutes. Okay, Azrifa and Shulian, can you please open the rooms for the participants? Where in 25 minutes we will call you back. Enjoy the analysis and the chat.
So, Ezzy, are you opening the rooms?
Azrifa might not be around. Okay, so let me just.
Yeah, sorry, I'm using
How many
my
of us
pad.
are here? Shulian, can you open the rooms?
Sorry, I'm using my pad, so I may not be able to open the rooms.
No problem.
Let me double check.
Create 28 divided by 7. 8.
Let's say 4 to 5.
Maybe 8 groups. Let's see how many people will go into each group. Okay, everybody. In 25 minutes, I'll call you back.
Okay.
Please join the groups now. Okay, the rooms are open. Okay, let's start our discussion. Group 1, what did you find in your discussion?
Hi. Actually, we ran our database, and I'm not sure whether we are doing the right thing.
Okay, so why didn't you share your screen? Can you share your screen with us?
Yeah, sure. So we first ran the output of the
map.
Yeah, the map. Yeah. So actually, is that are we doing the right thing?
Yes,
Yeah.
we're doing the right thing, the same thing. Yes.
Okay.
This is the rightest thing, the most right, or the rightest. I mean both.
Okay. 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 That's a really.
This is the right map, so it's the right thing.
Okay. So
So how do you interpret this map?
So the left side is the students that
Mhm.
in the test, and the rest is the items.
Good.
So obviously the item 5 is the most the difficult one,
Exactly.
and the item 1 is the easiest one.
Can you compare the means?
The means.
Now, the means of items versus the means of persons.
How do I do that? I'm sorry.
Does anyone from your group can help? Does anyone from Steve's group help?
I think here item 7, it means the mean, right?
Yeah, because just beside the M.
Yes.
Oh.
And the item above item 7 means that the difficulty of these items are more difficult than item 7. And items below 7, it means these items are easier than item 7.
Yeah, excellent. Precisely. So item 7 happens to be right at the mean of the item difficulty. So it provides a threshold above which items are more difficult than the mean, and below which the items are less difficult than the mean or the easier. How about the mean in persons? Yeah.
I'm not very sure, but I think that the person above this 0, it means that they are above the main level, the main ability level. But the person that under 0 is that under the mean is that they didn't.
Under 0 or under mean for persons? Under mean for persons, right?
Yeah, I'm sorry.
Yeah.
Persons. Okay. And the main for person here, they actually the below person, they are
Less
not
able than the mean.
yes, less able than the mean level person.
Exactly. Now, can you compare the mean of persons with mean of items? What do you conclude?
I think the main person, it means that they can do the item 7 and the item below 7 right. The possibility they do this item right is very high.
Yeah.
But above item 7, they may do it wrong.
Who? For who?
The main level, the ability.
Oh, I see. I see. Okay, so let's pause here for a while, and let me ask if someone else wants to add to it. I mean, about compare. So far, you have been correct. You have been on right track. Just accept the last point that you raised.
I'm sorry, Dr. Vahid.
Yeah.
Can I raise a question?
Sure.
So the mean of the item is higher than the mean of the students.
Precisely.
So is that means that students don't have the average ability to get the item right? Precisely.
That's what I was looking for, meaning that this test on average is more difficult for these people. Okay. Right? That's how you would want to put it. So because the mean of the items is above the mean of the persons. And that's how we can compare them. And this comparison, by the way, guys, can only be done using rush analysis. Doesn't make sense to compare the means of items and persons if you're not doing rush analysis. But this is one of the fantastic things about rush analysis. So by just looking at this map, you can find out whether the items are of the right ability, right difficulty level for the persons. So Steve, you put it correctly, yes. As you see, the overwhelming majority of people, of persons on the left side, are below the mean of the items. They're below 0. right? So that's another piece of evidence for you that this test is really difficult for these people. So we have created a difficult test. But of course, when we were creating this test, what we had in mind was the population of secondary school students in Singapore. And this is just from 2 schools. So I'm not sure if our data is very representative of all Singaporean students. So maybe in a larger sample, the difficulty would change. Okay, everybody. Any questions about this?
Sorry, Dr. Vahid. I have a question.
Sure, sure.
So I would like to check if I understand it in the right way. So for the left side, yes, there are lots of X, which means the student's ability. So for item 5 and item 9, so does it mean that the students they are estimated that, or they're supposed that they do not have the ability to answer question item 5 and item 9 because they're too difficult?
Yes, exactly. You're absolutely right. Just the way that we use terminologies in Roche is more probabilistic rather than certain. So this is how you would put it. You would say that on average, the students are less likely to answer item 5 and item 9.
Yeah, but
we're talking about probability.
Okay, yeah. So it does not mean that the students cannot answer the question, because based on that table, there are students who can solve this.
Absolutely,
item.
absolutely.
Okay. Thank you.
Yeah. So for example, the last X on top of all X's, can you see X on top? Yeah, that one. Yeah. He has some chance because he's very close to item 9, but the chances are still not that high. So we're not saying that this person will answer the question for sure, but probabilistically, there's less likelihood that this person will answer the question correctly. So every X stands for perhaps one person or more than one, maybe more than one person. Can you scroll down a little bit, Steve? One more. Okay. Probably every X stands for one person. Oh, okay. Did you use the entire data that I sent you? Did you use the main WinSteps?
Main WinSteps?
Yeah, because it seems that you have installed the trial version.
Yeah, I think so.
Yeah.
Yeah.
Yeah, can you close this and go back to, anyway, so because the input at the bottom of this table reads 75 persons, but there were more than 75 people, right? There were about 200 plus, if I'm not wrong.
239?
Yeah, so for you, only 75 people were analyzed. This is because you're using the trial version of WinSteps. If you use the version that I sent you, you would have gotten all the people in the data in your data analysis.
Oh, okay.
Yeah. Okay. Yeah. So group
zero. Dr. Vahid, you haven't explained the zero.
Sorry.
Zero. Yeah, there's only one line of numbers. It's about the item difficulty or the ability of the students.
Oh, so this is both.
Both.
It's a measure for both item difficulty and item and person ability.
But the person ability seems like the mean is below that, and seems like they're unleveled. They're not on the same level.
Yeah, I mean the scale on the left-hand side, 2, 1, 0, -1, that's for both persons and items. But persons and items have their own mean scores. The mean for persons is small, is below -1. Can you see?
Yeah.
And the mean for items is above that. It's 0.
So it's like 0 to me is like the mean. So which mean it is?
mean of items because it's on the right hand side. You see that the M's, one of them falls on the right side of the line. One of them falls on the left side of the line. So the one on the right is for items. The one on the left is for persons.
So the number, I mean, the Arabian numbers 0, 1, 2, this refers to the item difficulty, right?
The column on the left side, the most left.
I mean, yeah, this Arabian numbers, -1, 0, 1.
So that's the scale. So that's the logits. You can use that for both persons and items. So let me give an example. Can I share my screen? I think that will be easier. Let me. Gosh. Sorry, where is my screen? Okay, so I'm sharing my screen. Can you see it? It's the first data set I analyzed. Can you see it?
Yeah.
Everybody? Okay. Now let's say, so these are the logits, 0 logits. That's the scale. So the scale can be used for both people and the items. It's like their units. The units are like, for example, in kilogram or in grams or milligrams, something like that. So it's called logits. It refers to both the person and item. So you can say the person here, for example, these people are 0 logit able, okay? And at the same time, you can say that this item is also 0 logit difficult because they are right on 0. Everybody is on 0. Now, between 0 and -1, there are some numbers that are not mentioned, but there are some people who are on -1 logit difficulty. There is no item that is -1 logit. Sorry, I corrected again. -1 logit ability, but there are no items that are at -1 logit difficulty. Difficulty is this side. Okay, now comparing means, because now we have the same units, both of them are like kilograms or milligrams or logits, something like that. They can be compared because they're the same thing. So you can compare mean of items with mean of persons directly. So you can say the mean of the items is above that of the items, the other way around. Mean of the items is above the mean of the person. It's becoming a tongue twister. Do you get what I mean?
So I think the zeros, they represent the item difficulty, right?
No, both item difficulty and person ability.
But person ability is like below that.
This one, do you mean this M?
Left M. The left M, representing the person's mean ability, it's minus. It's below the 0. So it's like the 0 basically is used to refer to the item difficulty. So the 0 logit difficulty.
Oh yeah, I see what you mean. Yeah, this M, which is at 0 logit, refers to item difficulty.
Yeah.
But this M is not 0 logits anyway. It's minus something logits. Can you see the distance? Yeah. But what I was saying was, if you compare, for example, these guys who are at 0 with this item, which is at 2, you can say that these guys have little chance to answer this item. Why? Because it's way above their difficulty. It's way above their ability level. That's am I answering your question?
Yes.
Okay.
Thank
you. Good. Nice. Thank you. Okay. Group 5. Good. Who is in group 5?
Yes. I'm in the group 5.
Oh, Hangjun. Okay.
From the table, we can say that the result of the test difficulty is the same with the right map, right? And we can find that the SE and of the each test items can be saved from here.
Okay.
And we needed to say whether.
Can you interpret the SE first?
It means the mean score or the interval of the mean score. And for example, for the test item 5 and the mean score for the population will be ranged from the 1.96 plus or minus 0.14.
Excellent. Very good. Believe it or not, Hangjun, not many people in the field of language assessment can interpret it the way that you did. Well done on that. Okay. Go ahead.
And we also need to say whether each item represented the accurate difficulty of the each test item. We needed to say whether it belongs to the 0.5 to 1.5, as we can say that all of these 15 items all accurately represented the difficulty.
Good. So what you're saying is that we deserve a round of applause for creating these reliable and valid items.
Yes.
Good. Thanks for saying that. Okay, so you think that there's no problem in these items because everything falls between input and output mean square values fall between 0.5 and 1.5.
Yes.
Excellent. Does anyone have any questions, everybody?
Why our tables are not like still neater table?
Okay, because you have chosen a different font size, a font type. The font that you should choose is
where to choose it?
Font regular is Consolas. Okay, I'm gonna show you. Okay, so I'm gonna share my screen, everybody. Okay, so no, that's the email I sent you. Okay, so here's your output, right? So go to Format, Font.
Font?
Yeah, Format, Font, and choose Consolas. And click OK. You should work. Did you manage to get it? Or you should perhaps highlight everything. Format, Font, Consolas, regular 11. You can make it smaller if you like, for example, 10. Yeah, it works. It works for me. So it should work for you too.
Works.
Good.
Yeah. Works. Yeah, good.
Okay, so nice. Okay, since we have already run out of time, just wanted to mention about unidimensionality. It's a very difficult concept, honestly. In this course, I always get up to here, and when I want to talk about unidimensionality, I don't find time. Yeah, I will at least need half an hour more in. I think that's way beyond the scope of this course. So guys, I think that's just a good enough understanding of the basics of Rush measurement. Remember, those are the first few things that you need to churn out when you are doing Rush analysis. And now if you read papers, you will find that they mostly report these values. You should be able to make sense of them. The only thing we didn't cover was the idea of unidimensionality And I would be honest with you, look at the papers, the paper we publish in language testing. Not many people in rush measurement, not many people in language assessment who do rush analysis report any evidence for unidimensionality and local independence, which is a pity, because it's very important in rush analysis to make sure that your data is unidimensional and locally independent. But anyway, that means that you have, you know, acceptable skills now to be able to read and understand rush measurement papers, which is all about difficulty, standard error, in-fit mean square, out-fit mean square. That's the most important thing you need to know. Okay, so let's call it a day and take a break maybe, since it's already 9:02. Any questions before I close this session?
If you know about the item difficulty, if we just look at the scores, right? So if there's a mean score for everyone is already very like below, than is what is expected, then isn't that a proof already to show the difficulty is beyond the ability? Why do we need the rush analysis to confirm that?
So because that's only one of the basic things about a test. Importantly, we need to make sure that the difficulty measures are accurate or not, and that's the fit indices. If they're not accurate, that hierarchy that you see, items and people, the right map, doesn't make any sense. So the student scores do not make much sense. Item difficulties do not make much sense. Rush measurement validates it for us.
Okay.
Yeah, so it also gives us SE, standard error. It also tells us with what precision, with what certainty did you estimate the difficulty of this item, or with what certainty did you estimate the ability of each person?
Oh, it gives us more like predictability or visibility.
Yeah, so exactly. The term they use is psychometric validity. It provides evidence of psychometric validity. So if you have had a chance to go through the actual test items that I sent you, I think either Azrifa or Shulian shared with you.
Speaking English test items.
No, there was another test which I sent you. Anyway, so if you go through that, I think the items are available. You see, we have created those items based on a theory, and we anticipated that some items would be easy, some items would be difficult, the other way around, difficult, easy. And some of our predictions came true, which means that the theory was working fine, but not for all items. So it means that for some items, there was something else that was working and making the items more difficult, and we were not aware of that. But it helps us to make our understanding of the test more accurate.
Oh, Dr. Vahid, you just said you will explain the STD to us.
So STD is, I think I explained it enough. Look, it's the amount of precision that you have. So I think what I didn't explain was, why is it that when items are very difficult or very easy, there is high SE or standard error, right? The reason is that if, for example, if this is an item, okay, let's say, and this is a test item, and now I ask you guys to lift it. It's very difficult to lift it. Let's say it's very heavy and nobody can lift it. Let's say 10 people attempt to lift it and 9 of you fail. Only 1 of you can lift it. Now, this is not a very good measurement. Why? Because I'm giving you an item which is so difficult that I cannot get any useful information about your ability. I should give you items in which some people fail and some people do not fail. There is a good balance between fail and not fail. And when there's a good balance between them, then I can rely on that item for this group of people. Because if it's very easy, I will not be able to find out the threshold of your ability. And if it's very difficult in the same way, I will not be able to find out ultimately how much you can do, because all the things that I throw at you are too difficult to do, but you are able to do something. So I should give you some items that you can do something. I say, okay, so you fall within this range, not this range. But if all items are here, then and you are here, then you keep missing those items because they're very difficult. So standard error goes up.
So do we need to report it?
Report SE?
Yeah.
Definitely. Yeah, definitely. You should.
So the range is to plus that, right?
Yes, plus minus standard error. Yeah, but there's no range. I mean, the smaller the better. If you are creating a high stakes test or a very important test, I would say I would really love to see a standard error of 0.01. In some cases, I have seen 0. There's no error. That's perfect. That's just the right item for that group of people.
Some of these are like quite big.
0.14, 0.15.
0.51, 0.0, sorry, 0.51, 0. Something like that. Not like 0.01.
Yeah, I mean, sometimes they can be very big.
So does that mean it's invalid?
No, it means that precision of that item difficulty is not high.
Okay.
Especially if I want to extrapolate to a population, I will say if a large population of people take this test and answer that test item, I don't know exactly where the item difficulty will reside. Is it here? Is it here? It's within an interval, a big interval. You said it's 0.51, so it's a large interval. So 0.51 on this side, 0.51 on this side. There's a large interval, you know. So I don't know where that test item would fall. Well, now assume that for the same test item, we have a very small interval of 0.01. It means we are very close to the difficulty level in a population.
Yeah, so that's what I want to find out if we report that, and that's like already past that, like a 0.01 kind of criteria. So do we not like admit this is not very successful?
No, we don't. I mean, it doesn't mean that you have bad data. There are many reasons why we could get high standard errors. One of them is that, for example, you just started teaching this group of people. You just started and they don't know much about this thing. So you give them a pre-test. So then you see that the test is very difficult for them.
Okay.
And that is expected. I expect to get high standard errors. But as you move towards the end of the semester, for example, and your students become more able, this gap between items and persons becomes closer, and finally is closed. Then this is where the standard error of measurement becomes smaller, or this vanishes. So this is another way of looking at how students progress over time, because the test, which was very difficult at the beginning, became increasingly easier over time. And when you gave the same test at the end of the semester to your students, they managed to answer all the questions correctly, or many of the questions correctly. So that's a good thing.
So it can be used to assess the progress.
Yeah, specifically. That's one of the things you could.
Thank you.
Sure. I suppose no one else has a question. Does anyone have any questions?
Professor, what does T mean in the right map?
Sorry, T?
T, yeah, T in the right map. What does it mean?
T in the right map means 2 standard deviations. S means 1 standard deviation.
Oh, right, I see.
Yeah, it's a unit. You're welcome. And by the way, I have explained these in a lot more details in my videos. I hope you will watch those videos once again. Yeah. Anyway, so no more questions. Excellent. Okay, have a good evening, everybody. Or I should say good midnight.
Thank you.